للعالمين.
All right, this is CS50, and this is week 4. And if you think back a few weeks ago already, in week 0, we started talking about like what images are. And we talked about representation of images as this grid of pixels, and each pixel has like some pattern of bits that defines its color. Well, it turns out today we'll take a deeper look underneath the hood at how things like images and so much more is actually implemented using just these zeros and ones, and how now, as a programmer, you can actually harness that, for better or for worse, to better understand and better manipulate what's going on inside of a computer's memory using a language like C. In fact, even this bowl of stress balls that we keep happening is just a photograph, of course. But if you think back to week 0, if you sort of enhance this image, like they do in the movies, it actually doesn't work out the way you would think from Hollywood. As I continue to zoom in and zoom in and zoom in on a screen like this, you'll see that, yes, it gets bigger. But if it gets too big, what do you start to notice? The so-called pixelation. And indeed, you can see the individual dots. So next time you watch some show or movie on TV that has this sort of notion of enhancing, there's actually a finite limit there. You can only enhance so far as there's actually information there. But once you zoom into a certain level like this, like that's all that's there. You're not going to see the glint of the suspect in some crime drama in their eye just because you've enhanced the image. There's only a finite amount of information actually there. But we'll see today, too, that by understanding what's going on inside of a computer's memory, we can start to represent and even create and code more interesting things. So for instance, here is a bitmap, if you will, which is a term of art. A bitmap is a type of image. And it's a map of bits in the sense that you have this coordinate system of top, down, left, right, at least in this artist representation here. And suppose that maybe we all decide as the world that 1 shall represent the color white and 0 shall represent the color black. What might this map of bits, this bitmap, actually be? Can you see through it? Yeah. It is indeed a smiley face. So an amazing eye. If I actually turn all of the ones to white just to visualize this, you'll see indeed this is what was embedded there. But of course, on our computer monitors and phones, we have this grid of squares, this grid of pixels. So indeed, if you were to actually see on your screen a smiley face, like a black and white one at that, what's probably going on underneath the hood is just some pattern of zeros and ones and maybe single bits, 1-bit color, if you will, where 1 here represents white and 0 represents black. So if you kind of like this thing, it turns out you can do pretty beautiful, pretty interesting, pretty artistically inclined things. If you go to this URL at your leisure, cs50.ly/art, it'll actually redirect you to a Google spreadsheet that we've made in advance. And we've kind of shrunk the rows and columns to resemble a grid of pixels, tiny little squares, all of which are white by default, not unlike this easel here that we have a couple of volunteers working away at. In fact, would you guys like to come forward for a moment and say a quick hello before we come back to you?
Hello, my name is Daniel. I'm from Chicago.
Welcome to Daniel. And?
Hi, everyone. I'm Adam, and I'm from Trinidad and Tobago.
Nice. Well, welcome to you both. Thank you. You'll see that in their hands are actually a whole bunch of pixels, Post-it notes that we've handed them in advance. So if you don't mind, we'll come back to you in a couple of minutes and see what they've created, if you will, on this grid of white paper, much like you could create on this Google spreadsheet. In fact, feel free to send us your creations, if so inclined, via the URL you'll get at cs50.ly/art. Now, let's come back to week 0, where we defined some of the building blocks for images. We talked about RGB, which is just red, green, blue. And it's just one of the systems, a popular system via which you can represent any color of the rainbow using some combination of red and green and blue. And if any of you are artistically inclined or have used Photoshop or similar programs, you might typically have some means of selecting a color via some grid like this. But down here, notice, there's explicit mentions of the types of color systems in use, RGB. And in fact, here you see 0, 0, 0. And up here under new, you see the color black. And that implies that if you have no red, no green, no blue, well, that indeed would represent, by convention, the color black. By contrast, if we play around with Photoshop or any similar program, if you have a lot of red, a lot of green, and a lot of blue, for instance, 255, 255, 255, like really crank it up to the max value you can represent with 8 bits per week 0, well, then it turns out you get the color white here. And we can play with these numbers endlessly. For instance, if we use 255 of red, but 0 green and 0 blue, not surprisingly, the square at the top of the screen becomes, of course, red entirely, because it's all red and no green, no blue. If we change it instead to 255 for green, but 0 for red and blue, of course, we get green. And then lastly, if we crank up the blue, but leave red and green as 0, we, of course, get blue. But all this while, down here highlighted, is something that maybe some of you have seen before, like some combination of numbers and letters. If any of you have made personal web pages or used programs like Photoshop, you might have used these so-called color codes. So indeed, the world has this convention whereby using 6 digits, or sometimes 3, you can represent a little more succinctly some amount of red, green, blue. And you'll see here, maybe by inference, that if RGB is 0, 0, 255 respectively, perhaps where we're going with this is that 0, 0, 0, 0, FF is just an alternative way of expressing the exact same idea. No red, no green, and a lot of blue. But why is that? And in fact, we'll come full circle here to introducing something that we could have done in week 0, but it doesn't really solve a problem then. But today, as we focus more on images and on memory itself, turns out understanding these patterns is pretty useful. So back in week 0, we talked, of course, about binary. And binary, by implying 2, only gives you 2 digits, 0 and 1. You and I, as humans, almost always use the decimal system in normal conversation, dec meaning 10. So we have 0 through 9 instead. If a human like us wants to count up as high as 10 or 11 or 12, we don't have a digit per se for 10, 11, and 12. We start reusing digits. So it's 1, 0, 1, 1, 1, 2, and so forth. But in other systems, not binary, not decimal, but systems called hexadecimal, hex implying 16, there are actually more digits than these, which might come as a surprise. It's not pairs of digits, like in decimal, single digits. And frankly, it doesn't really matter what the digits are, because at the end of the day, these are just symbols that you and I immediately associate with some notion of math, but just strokes on the screen that represent some actual value. So it turns out that by convention, when you want more than 10 digits, 0 through 9, you start using letters of the English alphabet, A, B, C, D, E, and F. And you can represent them in lowercase. It's case insensitive, so it doesn't really matter. You might see it in uppercase or lowercase. But this is how you can count beyond 9, not using decimal, but using indeed something called hexadecimal. If we get really technical, this is also known as base 16. And it's the same idea as week 0, where instead of using base 2 for binary, base 10 for decimal, you use 16 as the base for hexadecimal. And so if we run through just some simple examples here, in the world of hexadecimal, your columns are just powers of 16. 16 to the 0, 16 to the 1, 16 to the 2, and so forth. But in the world of hex, we usually, at least thus far, and today, we'll see just pairs of digits like this. So here, for instance, is the 1s column and the 16s column, if we multiply that out. So if you wanted to represent the number you and I know in the real world as 0, in hexadecimal, it would just be 0, 0. If you want to represent the number 1, it would be 0, 1. And from there, we get 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9. Now things get potentially interesting. In decimal, it would obviously become 10. But in hexadecimal, it just becomes 0a and then 0b. Which is to say, if I rewind, after 9 comes in hexadecimal. If I pronounce it in decimal, this is how you'd represent 10. This is how you'd represent 11, 12, 13, 14. And then lastly, in hexadecimal, the 16th value is f, which is just always going to represent 15. So how do we connect this to some of the past math? Well, once you get to 0f in hexadecimal, if f is the highest you can count, just like in decimal, 9 is the highest you can count, what comes next? If this is 15, I claim, how do I represent 16 in hexadecimal? With what pattern of symbols? What pattern of symbols for hexadecimal? Yeah. So 1, 0, not 10, even though you might read it like that as a typical human, but 1, 0. Because why? Well, even if this is completely new to you, the whole column system, the places are exactly the same intuitively. So you need a 1 in the 1's place and a 1 in the 16's place and a 0 in the 1's place. And we won't count all the way up to 255, but if we count a little higher, this would be 1, 0, aka 16 in decimal. This would be 1, 1, aka 17 in decimal, and then 18, 19, 20, and so forth, dot, dot, dot. And we can count all the way up to FF, because if F is the biggest digit in hexadecimal, FF is indeed as high as we can count. And if each F represents 15, well, let's just do the math like in week 0. So 16 times F plus 1 times F is how all of us learn to do math in grade school, even though not in hexadecimal. That's, of course, 16 times 15 plus 1 times 15. Multiply that out, you get 240 plus 15. And ergo, you can count as high as 255 using 2 hexadecimal digits. Now, this is not the kind of thing where like this is going to be an interesting exercise mentally to ever convert in your head. Generally, you'll get used to the fact that after 9 comes A, and the biggest digit is F. And you'll just start to see patterns like this in the worlds of Photoshop, web pages in a few weeks, and beyond. But like, why is hexadecimal useful? Like, why are we complicating the world and adding on top of decimal something else? Well, it turns out that a single decimal digit, like F, the biggest one, for instance, is 15. And here, let me just propose a bit of mental math. How many bits do you need to represent the number 15 in binary? If you've got the ones place, twos place, fours, and so forth, how many bits total? So fewer than 5 to count as high as 15, I think. But close. Someone else? Seeing a hand? Yeah. So 4 bits, I think, suffice. Because if you want to count as high as F, that is to say 15, I think if you have 4 bits, you can do that. Because if over here is the ones place from week 0 for binary, this is the twos place, this is the fours place, this is the eights place, do out some quick math. So 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So it turns out that by convenience, hexadecimal digits can just be represented consistently with 4 bits, or fewer, but 4. And 4, of course, is half of 8. And 8 is like everywhere. Like 8 bits is a byte, which is, again, just a convention we've seen. And so the reason that you see hexadecimal in the world of Photoshop and eventually web pages is it actually just maps really nicely to expressing binary numbers more succinctly with a fixed number of digits. So for instance, anytime you see 1111, 1111 in the world as binary, you know what? That's a little tedious to both say and write. You can represent more succinctly any group of 4 1 bits more succinctly in hexadecimal as just F. So 1111, 1111 in binary more succinctly and more commonly now in the world of Photoshop, memory, images, and the like is represented more succinctly as FF. And that's why, because it just maps really nicely to 4 bits. And so we can be a little more succinct. So any questions on hexadecimal, which is just another way of representing information, but using the same grade school approach? Yeah? Good question. If you represent 15 with F, it would use 4 bits. So base systems are really just a way for us humans on paper or on screens to represent information. If F represents the decimal number 15, the computer underneath the hood has to use 4 bits to represent it. So 1 hexadecimal digit, by convention, always implies 4 bits underneath the hood. So therefore, if you have 2 hexadecimal digits, like 00, that means 80 bits underneath the hood, like for red or for green. If you see FF, now we know that's 4 1 bits and another 4 1 bits. And if we do out the math, that's 255. That's why in Photoshop, 0000FF means no red, no green, and 255 of blue. And it's just way more succinct than writing out like, what, 8 plus 8 plus 8, 24 zeros and ones. And it's just cleaner than even using decimal when you're using units of 8, which, again, computers just use everywhere. So it's just another system. It's not one you need to dwell on very much. But again, it's fundamentally no different from binary or decimal. We're just using a slightly different base. Any other questions on hexadecimal? No? All right, well, we had this blank canvas here. And I think, are you two perhaps ready to reveal for the world what you've created? Do you want to go ahead and I'll swivel it around for you. All right, here we go. Big reveal. And today's pixel art. A round of applause if we can. Very nicely done. Well, thank you both. If you want to come up after and tear this off and bring it home, you're welcome to. And keep the Post-it notes, too. Well, thank you to our volunteers there. Let's now translate this to really more technical world where we're going to see and consider it more often. Because, in fact, sometimes when you've had error messages over the past few weeks from Clang, the compiler, you might have even seen evidence of hexadecimal. We didn't call it out. It wasn't useful to know at the time. But it turns out a lot of programs use, and a lot of code uses hexadecimal for those reasons of more succinct representation. So for instance, where else might we see it? Well, here's that picture we keep pulling up of our computer's memory. And each of these squares in this grid represents a byte, sort of top left to bottom right in the computer's memory. But again, just an artist's representation. A few weeks ago, I claimed that each of these bytes can be numbered, of course. Like this is byte 0 at top left, then byte 1, then byte 2, then byte 2 billion if you have 2 gigabytes of memory. And so we could just number them like this, 0 through 15 on up. 16, 17, 18, and so forth. But per the reasons earlier, it's just more common in computer systems and in software to actually use hexadecimal just to describe the locations of, the addresses of things in memory. So instead, a typical programmer or computer scientist would call these first 16 bytes 0 through F. Just because, but that's because it's a predictable number of bits. So if we keep going beyond that, you would get not 10, not 11, not 12, but in hexadecimal, 10, 11, 12, and so forth, all the way down on the screen to 1F. And if I shrunk this down or had a bigger monitor, we would see eventually 255 bytes later from the start, 255 as well. But there's a potential problem here with using hexadecimal in this way. There's an ambiguity. Can anyone imagine what can go wrong if we use hex to just simply describe locations in memory like this? Yeah. Yeah, like 10 might also be 10. And maybe if you're really thorough, OK, wait a minute, it can't be 10 because here's F over here. So it's obviously not decimal. But why create potential confusion, especially when you're collaborating, building something with someone? We want to avoid that ambiguity. And so the convention humans decided on years ago is that if you want to make clear that a number is in hexadecimal, just by convention, you prefix all of the digits with 0x. The x is not like another character. It's not like a 17th character. It's just a human convention of putting 0x to imply here comes hexadecimal. And now it's unambiguous. So now we see 0x10 obviously is not 10 as we know it in decimal, but rather it's the number that comes after a single f. So it's really the number in decimal 16. So 0x, anytime you see it, that's just a visual cue that what is ahead is actually hexadecimal. So let's now start playing around with this information. So here's a super simple line of code from week 1 where I'm just declaring a variable n, and I'm defining it to be the value 50. And this is out of context. We probably need a main function and all of that. But let's just rewind to week 1 where we actually saw code like this and do something useful with a line of code like this. So let me go over here to VS Code. And in VS Code, I'll create a program called, how about addresses, since the goal of this, the goal here is to just play around ultimately with a variable like n. And let me go ahead and do this. I'll include, how about standard io.h. I'll do int main void, so no command line arguments for now. Int n gets 50. And now so that we can do something mildly useful with it, let's just go use printf and print out with %i and then a new line, whatever that value of n is. So this is not going to be interesting per se. It's just week 1 stuff where I'm defining a variable and printing it out to the screen. So let me go down to my terminal window and do make addresses. No errors, so that's good. I'll do /addresses, and of course, I should see the number 50 here. Now, what's going on underneath the hood? Let's translate now code to really what's going on underneath the hood of the computer. So if this is our grid of memory, I don't necessarily know as the programmer, and I definitely don't care as the programmer where exactly it's ending up in memory. That's the whole point of using code. Let the computer figure this out. But at least conceptually, I know that by declaring a line of code like that, the number 50 ends up somewhere in the computer's memory, and it's assigned the name n, a symbol n, via which I, the programmer, can refer to it. And I very deliberately used 4 of these squares for what reason? What might be the reason for using 4 squares specifically? Yeah. Yeah, so an integer is 4 bytes. At least most of the time on modern systems, an integer is 4 bytes. On an older computer, it might just use 1 or maybe even 2 bytes. But here, by convention, we're almost always going to see 4 bytes. I don't know if it's going to end up here. It might end up over here. But for now, who cares? I just know that the computer can store the information in this way underneath the hood. So let's now introduce another feature of C that we haven't had occasion to use just yet that's going to allow us to start poking around the computer's memory, for better or for worse. And this is one of those situations where you're about to acquire a skill, a power that can actually come back to bite you. Because once you know how to start poking around a computer's memory, you can do very powerful things. And next week, we'll see what you can build in a computer's memory. But you can also screw up pretty easily and cause more of those segmentation faults that a few of you have already suffered. So with that said, let's just stipulate that, you know what, I don't care necessarily where the 50 is in memory, but I know it exists at some address in memory. And just so I have an easy address to pronounce, let's just suppose it lives at 0x123. So that's the address in memory in hexadecimal by convention, and that just happens to be where it ends up when I write that line of code. But it turns out C has some other operators we can use. When we've seen the asterisk before, the star, and we've used it for multiplication. But today we're going to use it for something more powerful. And we're also going to introduce an ampersand, which allows us to do something as well. The ampersand operator is going to allow us to get the address of a piece of data in memory. Like by literally putting ampersand before the name of a variable, C will tell you what address that variable lives at. Maybe it's 0x123, maybe it's 0x456, who knows? But that will give you back the answer. The star does the opposite. It sort of means go there. So using the star, otherwise known as the dereference operator, I can actually go to a specific address if I want. And we'll see what this means in code. So how can I leverage this in some mildly interesting way to start poking around, but eventually we'll use this primitive to build more interesting things. So let me go back to, say, VS Code here, and let me go ahead and do this. I'll clear my terminal to start fresh, and I'll introduce another format code for printf, %p. And for now, just take on faith that it is %p because, but %p is going to allow me to print the address of a variable if I additionally tell C, get the address of n. So I'm changing %i to %p, and that's just something you have to do when printing addresses for now. But I need to change an ampersand in front of the variable name, so I don't print n, the number 50. I print out something like 0x123. And it's not going to be as simple as that. We'll see on the screen, though, where it actually ended up in my code space's memory. So here we go. Down in my terminal, make addresses again to recompile. And now /addresses should reveal not the value of 50, but the address of 50. And there it is. It's pretty long. It's not quite as simple and pretty as 0x123, but there's the 0x, meaning here's a hexadecimal address. And it's 7F, FC, C784A04C. Suffice it to say, your code space, and even your Macs and PCs nowadays, have a lot of memory. That's why, in part, this address is so big, not as small as the thing on my slide. So this, at the moment, isn't that useful yet, but it introduces us to a concept that we'll now call pointers. And pointers are admittedly one of the more challenging aspects of C. And if in future life you tell friends that, oh, I took a class called CS50 and we learned C, like you'll probably get kind of a look at people like, why did you learn C? Or like, oh, C was hard. And it's largely because of this topic, which isn't to say that it's that hard to wrap your mind around, but it's definitely very different. And it's not a feature that you can harness in higher level languages that we'll see in class 2, like Python and Java and the like. C is about as close to the computer's hardware, so to speak, that you can get before things get actually scary. The so-called assembly language we saw in week 2 when I had to link and compile and assemble and all of that, like that gets really low level. And you really have to be an expert with the computer's CPU or brain to understand that. But with C, you can actually poke around the computer's memory and do powerful things with that. But again, with great power comes responsibility. It's very easy to break programs by misusing memory or just having a bug that touches memory in some way that you don't intend. So pointers, at the end of the day, are pretty much what we just saw. A pointer is really just a variable that contains the address of some value. A pointer is a variable that contains the address of some value, or more simply, it's fine to think of it as an address. A pointer is an address of something in the computer's memory. Now, what might we do to actualize this? Well, here's 2 lines of code. It turns out, by using our 2 new operators today, I can declare an int, call it n, and assign it a value like 50, just like before. If I want to store the address of n in a variable and not just print it immediately via printf, I can declare a variable, for instance, called p, but I could call it anything I want, like any variable. But because it's an address, it's not int p. It has to be int star p, so to speak. And the star here on the left-hand side of the equal sign is just a clue to C that means p is going to be a pointer. That is, p is going to be the address of what? The address of an integer. Now, technically, it's still an integer itself, right? Because an address is just a number, whether it's 123 or OX123. So this is really just a semantic difference. So int star p just means that this variable doesn't contain any old number, like 50. It specifically contains a number that is the address of something else. So how can I now use this? Well, let me go back to VS Code, and let me propose that we add a line of code like that. So instead of just directly printing out that value, let's go ahead and define a second variable called p that's of type int star p, set it equal to ampersand n, and then this time, let's not just print out ampersand n, let's actually print out the value of p. So the only two new things here, if I zoom in, are I've used not only the ampersand on the right to get the address of n, I'm now using the star on the left to tell C that p is still a variable as always, but it's a pointer. It is the address of some other value like this. And I'm still going to print it with the same format code, %p, so that doesn't change. So let me go ahead and zoom out and do make addresses and /addresses. And there it is, exactly the same thing. Now, in and of itself, not that useful yet, but the fact that you can now access the addresses of things in memory means that we'll be able to build things and construct things and link things together by knowing where they live, so to speak. So any questions on this technique thus far? Yeah? OK. A good question. On line 6, must it be star p and ampersand? And in this case, yes, because what am I doing? On the left, and I'll get rid of the equal sign for now, this would give me a variable called p that's not an integer per se, but that's the address of an integer. But without the equal sign, I'm not storing anything in that variable. So by adding the equal sign and then ampersand n, I am explicitly figuring out with ampersand what the address of n is, which already exists per line 5, and tucking it away in this new variable called p. Other questions? Yeah? Good question. Every time I run the program, it uses up a different piece of memory. Short answer, yes. Computers, though, long story short, also have something called virtual memory. So if you run it again and again, you might actually see the same addresses on the same Mac or PC or cloud-based server. But we'll see in a bit where, at a high level, it's laid out. But it will always exist at some address. Good question. Yeah? Correct. Ampersand n is the address of n, and int star p is a pointer called p. And honestly, in an ideal world, if C were made today and not decades ago when humans were first creating languages, ideally, we would just have a data type called pointer. And then this would be a little less complicated because it would literally be what it says. The humans who invented C didn't do this, but this is the idea. So pointer is not a legitimate word in the code. It is a term of art in English. But this is really just the idea. But the way you express pointer as a data type is a little more cryptic as int star p here. But notice, in line 7, when I print out p, I don't use a star. I don't use an ampersand. Why? I literally just want to print the value of p. And we've been doing that since week 1. If you want to print a variable, just describe the variable by its name. No special syntax. Any other questions on this thus far? What's the advantage of using pointers? With pointers, we'll see today some applications of them. Really, the idea is going to come to fruition next week when we're going to create what are called data structures in memory, where we can build not just, for instance, one-dimensional data structures like an array. We'll see next week we can actually create the equivalent of two-dimensional data structures or even three-dimensional data structures by using these addresses and sort of linking things together. And we'll see the beginnings of that this week. But for now, focus, at least for now, on just really the syntax and what these building blocks can do for us. does the p pointer have to be point to an integer? Short answer, no. And we'll come back to this. For now, for the sake of discussion, we're only dealing with integers, like the number 50. You mentioned strings or characters. Absolutely. We're about to go there soon. So you can use the address of anything you want in the computer's memory. So in fact, let's translate this now to just the same picture, just to help you wrap your minds around what these two lines of code really fundamentally are doing. So if I come back to my grid of memory here, let's plop the number 50 in the variable n at the bottom right, like it was before. So this is that first line of code as before. But with the new second line of code, as soon as I create p, what do? Well, first, remember that n lives somewhere in the computer's memory. Usually, I don't care precisely where it is. But for the sake of discussion, let's suppose it's at 0x123, which is easier to say than where it actually ended up. And now, what is p? Well, p is just another variable. And variables live in memory, too. So let me just hypothesize that p lives up here. And it turns out that p, once you assign it, the value of ampersand n means that c will take a look at the variable n, realize, oh, it lives at 0x123. And what goes in the value of p is literally 0x123. So again, it's still an integer, which is confusing. But it's technically an integer being used as an address. And now just a prompt here. Notice that this pointer is pretty darn big. It's like 8 squares. What's the implication of that? Because I did that deliberately. How big must a pointer apparently be in most modern systems, would you say? Sure?
Pointers have big, so computers today have big memories.
Yes?
So we need a lot of space, a lot of bits to represent those spaces.
OK, good. Computers today are very big. You have gigabytes of RAM in your computer. You therefore need big pointers to be able to point at memory that's conceptually pretty far away. So to be clear, how many bytes does a pointer apparently take up? Well, it seems to take up 8 in total. Integers by convention nowadays are usually 4. Pointers, though, nowadays are typically 8 in this case. So I'm drawing it in a manner consistent with the reality, even though at the end of the day, it's not really that interesting what values are in here. In fact, let's emerge from these weeds. I don't really care what else is going on in my computer's memory at the moment, because I've only got those 2 lines of juicy code defining n and defining p. So let's hide all of the other squares. And honestly, I mean it when I say that programmers need to know that a variable exists somewhere in memory and needs to be able to get that address using like the ampersand. But you're never going to printf like I did the actual address. Like it's not generally interesting unless you're debugging your code. But you're not going to like start typing out crazy OX numbers in your code to move things around. You just need to know that the computer can figure out where things are. So frankly, by that logic, who cares that it's 0x123, right? Tomorrow it could be 0x456 or something else. So one of the ways to think of a pointer is literally as a variable that points at something else. And indeed, in this case, p, yeah, technically it has an address. And yeah, technically it's 0x123 in the story. But honestly, who cares? I just need to know that using p, I can get to the value n. And so what are these addresses? And in fact, if Carter wouldn't mind joining me up here for a moment, what are these addresses? Well, just like in our human world, we have mailboxes, even though you might not check it very frequently nowadays. But to get physical mail, every home, every business has a unique address. The Science and Engineering Complex is 150 Western Avenue, Austin, Massachusetts, 02134 USA. And theoretically, that uniquely identifies that building in the world. Well, here we have 2 mailboxes. Over here, we have a value n that happens to live, I'll claim, at address 0x123. And then over here, I claim there's another address called by name p. I don't actually care where it is, even though it definitely exists somewhere in the computer's memory. But if this is p, which is a variable, and that's n, another variable, ideally, this mailbox would be twice as big because of the number of bytes using, but Home Depot only had identical size mailboxes. But here is p, one variable. There is n, another variable. If I open up this mailbox, what should I find inside of it based on our story thus far? Like what value will I pull out dramatically in just a moment? Yeah, I think OX123. Now, using this, you can kind of think of this as like X marks the spot, no pun intended, where I can now like walk around the computer's memory and find my way to that location by sort of following the treasure map. Or if I want to more dramatically, thanks to our little Yale foam finger here, you can think of it more abstractly as p is just pointing at n. OK, that's not going over well. So let's switch over to the Harvard one. So p is pointing. So P is pointing at N, and so it turns out we will be able to write code now that will do the equivalent of me walking over to N. But for now, Carter, if you want to reveal what's in the mailbox, we should see, indeed, the number 50. So that's really all that's, oh, I feel Carter's waiting for applause. So like really, well, nicely done. Thank you. So that's just like a physical metaphor of what's going on here. In one variable, we have an address, and that variable by convention is called a pointer. In the other variable, per week 1, we just have a value like n. And you can, yes, follow the map and walk yourself to that particular address. And we'll see how to do that in code. But what's really interesting is this abstraction, that pointers literally, or really, I guess, figuratively, point at some other value in memory. All right, questions then on pointers in this form. Can pointers point to each other? So yes, there's things called double pointers. We're not going to see them anytime soon, but using star star, you can express an address of an address. But we won't see that just yet. Other questions on pointers? Yeah, in front. Are arrays, so to summarize, are arrays then pointers? So short answer, there's a relationship, and we'll come back to that in a little bit. But arrays are technically different from pointers, but we're going to be able to blur the lines a little bit by using one like the other. But let me come back to that in just a bit of time. All right, so if we have now this mental model, if you will, of like what a pointer is in memory, I think we can start to peel back a layer of